Tonight, before you drift into sleep, I would like to invite you on a special journey, not to a distant country, not to the depths of the ocean, but to the farthest place that human imagination has ever reached toward, the edge of the universe. Since childhood, most of us have looked up at the night sky and asked a question that is both simple and profoundly deep. If we kept traveling toward the stars forever, would there eventually be a final point? Does the universe have an edge, an invisible boundary, or a mysterious emptiness beyond everything we know? Carl Jung believed that humanity's greatest questions are not only about the outer world, but also reflections of something deep within our own souls. And perhaps no question reflects that more clearly than our fascination with whatever lies beyond the furthest horizon. Because when we try to understand the edge of the universe, we are also trying to understand the limits of human perception itself. What is remarkable is that modern science has carried us farther than any generation before us. We have discovered that the so-called edge of the universe is not as simple as a wall or an ending point. Instead, it opens the door to mysteries even stranger. Galaxies we will never reach, regions of space whose light has never had enough time to arrive, invisible horizons created by time itself, and even the possibility that beyond our universe, other realities may exist. In tonight's story, we will travel together across billions of years of cosmic history, exploring the most astonishing truths about the edges of space and time, the origins of galaxies, dark matter, dark energy, and the ultimate fate of every star. If you enjoy gentle stories about science, philosophy, and the depths of the human mind through the perspective of Carl Gustav Jung, take a moment to subscribe to the channel and turn on notifications. And now, take a slow breath. Relax your shoulders. Allow the thoughts of the day to gradually settle, because the journey to the edge of the universe is about to begin. Part 1. The journey to the edge of the universe. Tonight, as the world outside becomes quieter, as the sounds of a long day slowly retreat into darkness, I would like to invite you on a journey. Not a journey by train, not a journey by airplane, nor a voyage across oceans or through mountain ranges. This is a journey far stranger than any of those. A journey to a place that humanity has tried to reach with imagination for thousands of years. A journey to what we often call the edge of the universe. That phrase alone carries a special kind of fascination. The edge of the universe. It sounds as though somewhere out there exists a vast boundary, an invisible wall, a final cliff where space ends and something else begins. Perhaps many of us imagined exactly that when we were children. That if we could travel far enough, beyond the stars, beyond the galaxies, and continue onward forever, we would eventually arrive at a place marking the end of everything. A final door, a final limit, a final line between something and nothing. But what is fascinating is that the more scientists learn about the universe, the more they realize that this idea may not be correct, and perhaps that makes the universe even more mysterious rather than simpler. Because what we call the edge of the universe is not actually a place. It is not a location that can be marked on a map, not a coordinate in space, not a wall beyond distant galaxies. Instead, it is another kind of boundary, a more subtle one, a boundary that does not exist within the universe, but within our own capacity to perceive it. Carl Jung once wrote, "One does not become enlightened by imagining figures of light, but by making the darkness conscious." Perhaps the journey to the edge of the universe carries a similar meaning, for the most fascinating things are not what we know, but what we do not know. Not the regions of space we have observed, but the darkness that still lies beyond our reach. Since ancient times, human beings have looked up at the night sky. Hunters during the Stone Age did so. The builders of the pyramids did so. Ancient Greek philosophers, astronomers of the Renaissance, and modern physicists operating giant telescopes in space. All of them shared the same question. Where are we? And how vast is the universe? At first glance, this seems like a question about astronomy. But looked at more deeply, it is also a question of psychology, a profoundly human question. Because whenever we ask about our place in the universe, we are simultaneously asking about our place in existence itself. We want to know where we came from. We want to know what we belong to. We want to know whether there is some ultimate boundary. For the human mind loves boundaries. We live in rooms with walls, countries with borders, islands with coastlines, books with final pages. Everything familiar to us appears to have a beginning and an end. Yet the universe does not necessarily follow the rules to which the human brain has become accustomed. And that is where wonder begins. Today, modern observations suggest that the universe may be finite. But even if it is finite, that does not mean it has an edge. At first, this idea can be difficult to imagine. How can something be finite and yet have no boundary? One of the most famous analogies is the surface of Earth. Imagine that you are a two-dimensional being living on the surface of this planet. You could keep traveling forever, in any direction. You would never encounter an edge where the world suddenly ends. Yet that does not mean Earth's surface is infinite. It still has a definite size. It simply has no edge, no final border, no place where you could point and say, this is the end. Some cosmologists believe that space itself may work in a similar way. If so, the question, where is the edge of the universe, may be much like asking, where is the edge of Earth's surface? It may be a question created by our intuition rather than by the true nature of reality. But then another possibility emerges, an even stranger one. What if the universe is infinite? What if space extends forever in every direction? No beginning, no ending, no wall, no outside, no place to go beyond the universe. Because if the universe is everything that exists, then the concept of an outside may simply have no meaning. And this is where the human mind begins to feel overwhelmed. For we are born into a finite world, a world of distances, of objects, of dimensions, of limits. But the universe may not be like that at all. It may be so vast that ordinary intuition is no longer enough. And perhaps that is one reason the night sky always feels both beautiful and mysterious. For every star is more than a point of light. It is a reminder that reality is far greater than anything we can see. And as we continue this journey, we will discover that what people call the edge of the universe is not really the limit of space. It is the limit of light, the limit of time, and also the limit of perception. Because when we look farther into the universe, we are not merely looking farther through space, we are looking backward through time, and that will become the doorway to the next chapter of tonight's journey. Part 3. The expansion of space. At the end of the previous chapter, we stood before a deeply humbling idea that what we can see is not the entire universe, that beyond our observable horizon, there may still be countless galaxies, countless stars, and countless stories whose light will never have enough time to reach Earth. But as astronomers began to study that immense expanse more closely, they discovered something even stranger, something that completely transformed humanity's understanding of the cosmos. At first glance, most of us carry a fairly natural image of the Big Bang. We imagine a colossal explosion occurring somewhere in space, like a cosmic firework. From a central point, matter is blasted outward in every direction. Galaxies become fragments racing through emptiness, and over time, they drift farther and farther apart. It is a very intuitive picture, but surprisingly, it is not entirely correct. Reality is far stranger. Galaxies are not simply rushing through a pre-existing, motionless space. Space itself is changing. Space itself is expanding. The first time many people hear this, they find it difficult to imagine. Because in everyday life, we think of space as a motionless stage. Objects move upon it. Cars travel along roads. Airplanes cross the sky. People walk across the ground. Space is simply where things happen. But in modern cosmology, space is not a passive backdrop. It is part of the story, a character in motion, a structure capable of bending, vibrating, and expanding. Carl Jung once wrote, "The least of things with a meaning is worth more in life than the greatest of things without it." Perhaps the expansion of space is a beautiful example of this idea. For if we relied only on our eyes, we would never realize what is happening. The stars seem to remain fixed in place. The constellations appear much as they did thousands of years ago. Everything looks stable, quiet, still. Yet beneath that stillness, the entire universe is changing, without pause, without rest, like an extraordinarily slow melody that only the patient can hear. One of the most famous ways to explain this idea is with the image of a balloon. Imagine drawing tiny dots on the surface of an uninflated balloon. Each dot represents a galaxy. As the balloon expands, the dots move farther apart. What matters is that none of the dots are actually moving across the surface. The surface itself is expanding. The distance between the dots increases. Galaxies in the universe behave in much the same way, not because they are actively fleeing from one another, but because the very fabric of space between them is growing. This idea was first confirmed in the early 20th century by the American astronomer Edwin Hubble. While observing distant galaxies, he discovered something astonishing. Most galaxies appeared to be moving away from us. And not only that, the farther away a galaxy was, the faster it seemed to be receding. At first, this puzzled many scientists, but gradually, a new picture emerged. Earth was not sitting at the center of an explosion. The Milky Way was not somehow special. Rather, all of space was expanding everywhere at the same time. It is a beautiful idea, because it reminds us that the universe has no privileged center, no favored location, no point that can claim to be the center of everything. From any galaxy in the cosmos, an observer would see most other galaxies moving away. Every place appears to be the center, and precisely because of that, nowhere truly is. Jung spent much of his life studying the ego. He observed that human beings naturally tend to see themselves as the center of the world. Yet psychological maturity begins when we recognize that we are merely part of something greater. Astronomy offers a similar lesson. Each major discovery removes a little more of our sense of centrality. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The Milky Way is not the center of the universe. And perhaps that is exactly what makes the universe so wondrous. Not because it revolves around us, but because it does not. As measurements became increasingly precise, scientists realized that this expansion leads to an extraordinarily strange consequence. There are regions of the universe moving away from us faster than the speed of light. At first, this seems to violate physics. Isn't nothing supposed to move faster than light? In fact, that rule still holds true. No object can travel through space faster than light. But here, objects are not moving through space. Space itself is expanding. Imagine drawing two dots on a sheet of rubber and stretching the rubber. The distance between the dots can increase extremely rapidly, even though neither dot is running anywhere. This is one of those ideas that evokes both wonder and a faint sadness, because it means there are galaxies whose light will never reach us again. At this very moment, they may still appear in our telescopes. We can still see their ancient images, but the space between them and us is expanding too quickly. So quickly that any new signal sent today will never cross the ever-growing distance. In a sense, they have gradually drifted beyond the shared conversation of the universe, forever. And when we reflect upon that, it is difficult not to feel moved. For within that immeasurable vastness, there are islands of light we will never touch, never greet, never know as they exist in the present moment. They will continue to exist, yet forever remain beyond communication. And here, another question arises. If space has been expanding since the earliest moments of cosmic history, what caused it to begin? What initiated this immense unfolding? And how did the universe become so remarkably uniform when distant regions seem never to have had the opportunity to communicate with one another? To answer those questions, we must travel even farther back in time, far beyond the first galaxies, far beyond the oldest light we can see, back to an unimaginably brief moment after the Big Bang, a moment when space itself may have expanded at a rate almost impossible to comprehend. And that will be the next destination on our gentle journey tonight. A journey leading to one of the boldest ideas in modern cosmology, the theory of cosmic inflation, Part 4. The universe may be infinite. At the end of the previous chapter, we explored an idea that asks ordinary intuition to pause for a moment. Galaxies are not truly racing through a motionless void. Instead, space itself is expanding, like a vast cosmic fabric quietly stretching in every direction. And within that endless expansion, there are galaxies that have drifted so far away that any new light they emit will never be able to reach us again. A thought that is both beautiful and gently melancholic. But if we take one more step along this path, an even greater question appears. If space is expanding, what is it expanding into? Is there something outside it? Does the universe possess some ultimate boundary, or does it continue forever? This is one of humanity's oldest questions. Perhaps it has existed ever since our earliest ancestors first lifted their eyes toward the night sky. For the human brain evolved within a world of boundaries. We live in houses with walls, travel along roads with endings, see forests that meet the horizon, watch oceans reach the shore. Everything familiar has limits, and so our minds almost automatically assume that the universe must be the same. There must be a place where everything ends, a final edge, a final boundary, an invisible wall where space comes to a halt. Yet modern science leads us toward another possibility, a possibility far stranger, that the universe may have no edge at all. Carl Jung once wrote, "The pendulum of the mind oscillates between sense and nonsense, not between right and wrong." Perhaps no subject makes those words come alive more vividly than our attempts to imagine infinity. For infinity is both fascinating and bewildering to the human mind. We can say the word, write the symbol, place it inside equations, but truly imagining it is something entirely different. Our brains are designed to navigate finite distances, finite objects, finite experiences. Infinity lies beyond ordinary experience, and yet some of the best measurements humanity has ever made seem to point in that direction. When scientists study the cosmic microwave background radiation, observe the motions of galaxies, and measure the large-scale geometry of space, they discover something remarkable. Space appears to be extremely flat. That sounds simple, but flat here does not mean flat like a sheet of paper. It carries a deeper geometric meaning. Imagine living on the surface of an enormous sphere. If you travel in a straight line long enough, you eventually return to where you started. That surface is curved. By contrast, on a perfectly flat plane, parallel lines never meet. The angles of a triangle always add up to 180 degrees. The familiar Euclidean space taught in school is an example. Modern measurements suggest that our universe is extraordinarily close to that condition. Extremely flat. So flat that if curvature exists, it lies below our current ability to detect it. And this opens a breathtaking possibility. A flat universe may extend infinitely. No ending, no edge, no boundary, only space stretching onward forever. When I think about this, I often imagine a traveler walking across an endless plain. Each time he climbs a small hill, a new horizon appears. Each time he reaches what seems to be the end, he discovers more distance unfolding ahead, not because he has not traveled far enough, but because there is no final destination at all. Perhaps what makes this idea so powerful is not the physics, but its psychological effect. Jung believed that human beings are always searching for completion, a closed circle, a final answer, an ultimate meaning. But perhaps the universe is teaching us the opposite lesson. that some questions do not lead to a wall, they lead to a horizon. And every time we approach it, that horizon expands. For centuries, people asked, what lies beyond Earth? Then we discovered continents. Later we asked, what lies beyond the solar system? Then we discovered the galaxy. After that we asked, what lies beyond the Milky Way? And we found hundreds of billions of other galaxies. And now we ask, what lies beyond the universe? But perhaps this is the first time the question encounters a unique obstacle. It may be that the question itself no longer possesses physical meaning. Pause for a moment and feel the weight of that thought. If the universe is all of space and time, if it contains every place where the concept of where can exist, then what does the word outside truly mean? Ordinarily, when we ask what lies outside a room, we assume the room exists within a larger space. When we ask what lies beyond a nation, we assume that nation exists upon a larger world. But if the universe already contains all existing space, then there may be no larger space for it to exist within. In other words, the question, what is outside the universe, may resemble asking, what lies north of the North Pole? Or, where is the point to the left of every point? The language still functions. The question still sounds reasonable, yet the concepts within it may no longer correspond to any physical reality. This is one of those moments when science and philosophy meet. For when we reach the furthest limits of understanding, we begin to realize that many questions require more than new answers. They require new ways of thinking, and here, humility becomes an essential part of knowledge. Not every question can be answered in the way the human mind expects. Not every mystery leads to a final door waiting to be opened. Sometimes mysteries exist to remind us that reality is larger than our familiar patterns of thought. And then, amid all these reflections, an ancient light quietly waits for us. A light that does not come from stars, nor from galaxies, but from the childhood of the universe itself. A faint signal appearing in every direction across the sky. A remnant from a time when the entire cosmos was still young. And in the next chapter, we will encounter that extraordinary light, what scientists call the cosmic microwave background radiation, or, in a more poetic sense, the oldest baby picture of the universe that humanity has ever seen. Part 5. The Cosmic Microwave Background, CMB. At the end of the previous chapter, we found ourselves facing one of the greatest questions the human mind has ever asked. Does the universe have an end? Does space stretch on forever? Or is it finite, yet without boundaries? And then we realize that perhaps the strangest thing is not the answer itself, but the fact that these very questions are leading us to the limits of intuition. Yet while those reflections on infinity continue to drift somewhere among the stars, something else is quietly waiting for us. A very ancient light, older than every star, older than every galaxy, older than any planet that has ever existed. A light that began its journey when the universe was still very young, and after nearly 14 billion years of wandering through space, it is still arriving. Right now, in this very moment as you listen to these words, it is still there, covering the entire sky, present in every direction, gentle as a whisper from the earliest dawn of time. Scientists call it the cosmic microwave background, or more simply, the CMB. But if we step away for a moment from the language of physics and look through the eyes of imagination, perhaps we might call it something else, the baby picture of the universe. Carl Jung once wrote, "Every form of addiction is bad, no matter whether the narcotic be alcohol, morphine, or idealism." Yet throughout many of his works, Jung repeatedly returned to a beautiful idea, that in order to understand a person, we sometimes need to return to the earliest years of their life, their first experiences, their earliest traces, those original images that helped shape everything that came afterward. Interestingly, the universe seems to have a similar story. If we wish to understand why galaxies exist today, why stars exist, why there are planets, oceans, and even beings capable of contemplating their own origins, we must return to the childhood of the universe. We must go back to a time when everything was entirely different. When the Big Bang had only just occurred, the universe looked nothing like what we see today. There was no night sky, no constellations, no spiral galaxies, no blue planets. There was only an ocean of energy so hot that it is almost impossible to imagine. An environment so dense that light could not travel freely. This may sound strange. We often think of light as something that naturally moves through space. But in the early universe, matter and radiation were mixed together in a state of intensely hot chaos. Free electrons constantly collided with photons, like thick dust swirling inside a storm, scattering every ray of light. If it had somehow been possible to stand inside the universe at that time, which of course it was not, you would have seen nothing at all. Not because there was too little light, but because there was too much. So much that it could not travel very far. A beautiful paradox of nature. Sometimes, too much light creates darkness. Then time passed. Space continued to expand. The universe gradually cooled, little by little, until a special moment arrived, about 380,000 years after the Big Bang. Compared with the universe's present age of nearly 13.8 billion years, 380,000 years is scarcely more than infancy, like the first few hours in a human life. Yet it was during that moment that something profoundly important happened. The temperature dropped enough for electrons and protons to combine, forming the first hydrogen atoms. Suddenly, light was no longer trapped. Space became transparent. For the first time, photons were free to travel, and they began a journey lasting billions of years, a journey that continues even today. Those photons are what we now call the CMB. What makes this story so moving is the following. When modern telescopes observe the CMB, they are not merely detecting a physical signal. They are seeing the oldest light humanity has ever observed. Not light from a star, not light from a galaxy, but light from the childhood of the universe itself. A portrait captured when everything was only beginning. There is something deeply reminiscent of memory in this story. Jung devoted his life to studying how the past continues to live within the present. He believed that early experiences never truly disappear. They continue to shape us in invisible ways. In psychology, this is true for individuals. In cosmology, something remarkably similar appears to be true for the universe itself. For the tiny ripples present in the CMB billions of years ago have left their imprint upon the sky even today. When scientists examine the CMB carefully, they discover that it is not perfectly uniform. Some regions are slightly warmer, others are slightly cooler. The differences are extraordinarily small. So small that they are almost impossible to imagine. Yet those tiny differences carry immense significance, for they are the first seeds of cosmic structure. Regions that were slightly denser attracted additional matter. Those regions gradually grew under the influence of gravity. Then, hundreds of millions of years later, they became enormous clouds of gas, the first stars, the first galaxies, clusters of galaxies, and eventually the vast cosmic web we observe today. This always reminds me of an idea Jung often returned to, that the smallest things sometimes carry the greatest power to shape the future. A dream, a symbol, a passing thought, a childhood memory. Things that seem insignificant can sometimes become the foundation of an entire life. The universe appears to work in a similar way. Tiny fluctuations within the CMB became galaxies. Galaxies gave rise to stars. Stars forged the elements. The elements formed planets, and eventually, they formed us. In a very real sense, every human being is a descendant of those tiny ripples that existed within the background radiation at the dawn of time. We do not merely live within the universe. We were born from patterns that appeared within it, almost at the very beginning of cosmic history. And from that infant portrait, a new question begins to emerge. If the tiny variations in the CMB could give rise to all the structures we see today, where did those variations come from? Who planted those first seeds? What created those primordial ripples? To answer that question, we will need an even more powerful time machine. We must look beyond the CMB itself, back to a time when the universe was far younger, to an era when light could not yet travel freely. And there, we will encounter one of the most beautiful ideas in astronomy, that looking farther into space is actually looking farther back into history, that every telescope is not merely an instrument of observation, but a doorway into the past. And that will be the next destination on our gentle journey tonight. Part 6. Looking far away is looking into the past. At the end of the previous chapter, we stood before one of the oldest relics humanity has ever discovered, a faint glow, an echo remaining from the childhood of the universe. The cosmic microwave background, a picture taken when the universe was only about 380,000 years old. And as we gazed upon that picture, we suddenly realized something extraordinary. We are not merely observing space, we are observing time. At first, this may sound like a poetic statement, but in reality, it is one of the deepest truths of modern astronomy. Every time we look up at the night sky, we are looking into the past. Not metaphorically, but in a completely literal physical sense. Carl Jung once wrote, "Life really does begin at 40. Up until then, you are just doing research." I have always found something fascinating about placing those words beside cosmology, because the work of astronomers seems, in many ways, to be a journey into memory. They cannot step into the past. They cannot reverse the clock of time. Yet by looking farther into space, they can look deeper into history, like archaeologists digging through ancient layers of earth. Only their tools are not brushes and shovels. They are enormous telescopes. To understand this, let us return to the old companion that has accompanied us since the beginning of our journey: light. Light travels incredibly fast, so fast that in everyday life it feels almost instantaneous. But fast does not mean infinite. Even light requires time to travel from one place to another. When you look at the moon, its light has spent more than a second traveling to your eyes. When you look at the sun, that light left the sun's surface about 8 minutes earlier. If the sun was suddenly to disappear, a purely hypothetical scenario, we would continue seeing it for another 8 minutes. This sounds strange, yet it leads to a beautiful realization. We never see anything exactly as it is in the present moment. Everything arrives with a delay, a tiny separation in time, a memory carried by light. In everyday life, that delay is too small to notice, but within the universe, it becomes enormous. The nearest star beyond the Sun is Proxima Centauri. Its light takes more than 4 years to reach Earth. That means we are seeing Proxima Centauri as it was more than 4 years ago. Not now, not this moment, but an image sent from the past. If that star changed today, we would not yet know. We would have to wait another 4 years. And the farther we look, the greater the delay becomes. A galaxy 1 million light-years away appears as it existed 1 million years ago. A galaxy 1 billion light-years away appears as it existed 1 billion years ago. And the most distant galaxies humanity has ever observed appear as they existed more than 13 billion years ago. Before Earth existed, before the Sun was born, before the Milky Way acquired the familiar form we know today. This makes the telescope one of the strangest time machines ever created. In science fiction, a time machine is often imagined as a device that transports people into the past. But astronomy gives us a more realistic version. We do not travel into the past, we look into it. Every telescope is like a window opening onto a different era. Looking nearby means looking at recent time. Looking farther means looking deeper into ancient time. It is like standing inside an enormous library, except that instead of books arranged on shelves, the chapters of history are distributed throughout space. A nearby galaxy is a more recent chapter. A distant galaxy is an older chapter. a signal from the cosmic microwave background, is among the very first pages of the book. The universe reveals itself as a layered archive of history. Every distance represents an era. Every point of light is a memory. Every photon is a message sent from a distant past. And the remarkable thing is that those messages are still arriving, even now. Even as we sit quietly in a room on a small planet orbiting an ordinary star, there are photons whose journeys began before humanity existed, before the dinosaurs disappeared, before Earth hosted complex life, and after wandering for billions of years through almost empty space, they have finally arrived, touching a mirror inside a telescope, touching an electronic detector, and telling the story of time. Jung often spoke of the collective unconscious as a repository of humanity's ancient experiences, not personal memories, but deeper layers, structures accumulated across generations. In a very different way, the universe also seems to possess a memory of its own, not stored within a brain, not preserved in books, but carried within light. Light is the memory of the universe. Every photon carries traces of the place where it was born. It records temperature, chemical composition, motion, distance, like a sealed letter sent from the past, and astronomers devote their lives to learning how to read those letters. This leads us to a realization that is both beautiful and slightly melancholy. There are regions of the universe that we will never see as they exist today. When we observe a galaxy 10 billion light-years away, we do not see it as it is now. We see it as it was 10 billion years ago. Its present moment still lies somewhere within our future. The light carrying that present-day image is still traveling toward us. It may take billions more years to arrive. This means that the observable universe is actually a mosaic, assembled from many different eras. There is no single moment called now on the scale of the entire cosmos. We are witnessing countless moments simultaneously, some younger, some older, some telling the opening chapters, others telling the final pages. And the more we think about this, the more we realize that the observational horizon is not merely a boundary of distance, it is a boundary of time. When we reach distances so vast that light has not had enough time to arrive, we lose more than the ability to see farther. We lose the ability to look deeper into history. Yet at precisely that point, a new question begins to emerge. If we can see the history of the universe through light, what shaped that history in its earliest moments? What made the universe astonishingly flat? What caused its temperature to be nearly identical in every direction? And what planted the first seeds of future galaxies? To answer those questions, we must journey even farther back, to an unimaginably brief moment after the Big Bang, a time when space itself may have expanded faster than anything the human mind can truly imagine. And that will be our next destination. The story of cosmic inflation. Part 7. The theory of cosmic inflation. At the end of the previous chapter, we explored an idea that almost feels like a miracle, that whenever we look up at the night sky, we are not merely looking across distance. We are looking into history. Distant galaxies do not appear as they exist at this very moment. They appear as they existed billions of years ago. Every photon is a fragment of memory. Every ray of light is a letter sent from the past. And as scientists followed those letters farther and farther back, they gradually arrived at a profound question. A question born in the childhood of the universe itself. Why does the universe look the way it does? Why is it so vast? Why is its temperature almost identical in every direction? And why has the structure of galaxies emerged in such a remarkably orderly way? These questions lead us to one of the boldest ideas in modern physics, the theory of cosmic inflation. Cosmic inflation, a hypothesis so strange that when it was first proposed, many scientists found it difficult to believe. Yet at the same time, it explained phenomena that previous models could not. Carl Jung once wrote, "In all chaos there is a cosmos. In all disorder, a secret order." Whenever I read those words, I think of cosmic inflation, For this is precisely a story about how a moment of unimaginable chaos may have created the order of the universe we see today. To understand this, let us imagine that we can travel backward through time, not merely a few years, not merely a few centuries, but billions of years, back before galaxies existed, before the first stars ignited, before any planets had formed. Continue backward, further still, until the entire universe becomes a region of space so tiny that it is almost impossible to comprehend. In the earliest moments after the Big Bang, everything was utterly different from what exists today. There were no vast cosmic distances, no galaxy clusters separated by millions of light years, no night sky, no familiar concepts that we now use to understand the world. There was only energy, temperature, and conditions so extreme that they surpass anything humanity has ever recreated in an experiment. And then, according to inflationary theory, something extraordinary happened. During an unimaginably brief interval, so brief that if written as a number, it would contain a seemingly endless string of zeros after the decimal point. Space suddenly expanded at a staggering rate, not merely doubling, not growing 1,000 times larger, but expanding exponentially, like a tiny speck of dust suddenly swelling to the size of an entire galaxy in the blink of an eye. Of course, this is only an analogy. Reality is far stranger. The important thing to remember is that nothing was flying through space. Space itself was expanding. The very fabric of reality was being stretched, and during that brief instant, the entire infant universe was magnified to an enormous scale. At first, this may sound like a technical detail of physics, but in truth, it solves a profound mystery, a mystery known as the horizon problem. Think back to something we discussed earlier. Light requires time to travel. That means regions of the universe that are very far apart today may never have had the opportunity to exchange information. So why do they possess almost identical temperatures? If two rooms have never communicated with one another, why should their temperatures be nearly the same? For many years, this question puzzled cosmologists. Inflation offered a surprisingly elegant answer. It suggests that regions now separated by billions of light-years were once extremely close together, close enough to reach thermal equilibrium, close enough to be part of the same environment. Then inflation occurred. Space expanded enormously, like placing a tiny dot of ink on a sheet of paper and stretching that paper until it becomes the size of an entire stadium. Regions that were once neighbors became separated by unimaginable distances, yet they carried with them the memory of their original state. That explains why the sky appears so uniform. And then another mystery emerged. Why is space so flat? As we discussed earlier, modern measurements indicate that the curvature of the universe is so small that it is almost impossible to detect. This too was once a major puzzle, for even a tiny deviation in the earliest moments should have grown dramatically over time. Once again, inflation provides an answer. Imagine standing on the surface of Earth. On a planetary scale, Earth is a sphere. But if you examine only a very small region, the ground appears perfectly flat. Inflation works in a similar way. It stretches space so enormously that any original curvature becomes nearly impossible to notice, like magnifying a tiny patch of a balloon until it resembles an infinite plane. What makes inflation especially fascinating is that it does more than solve equations. It tells us a story in which the largest features of the universe today may have originated from the smallest conditions imaginable, a story that Jung might have found deeply familiar. For in his psychology, early experiences often exert profound influence over an entire lifetime. A small memory, a small image, a small symbol can quietly shape decades of what follows. The universe seems to work in much the same way. What happened during its earliest moments may have shaped every galaxy, every star, and every planet that appeared billions of years later. But then another question emerges. If inflation stretched space to such enormous scales, what else was stretched along with it? Were there tiny traces already present before inflation began? Were there microscopic fluctuations that became amplified? And could those fluctuations be the very first seeds of all the galaxies we see today? That will be the story of the next chapter. A story that begins with vibrations smaller than an atom. Quantum fluctuations so delicate that they seem almost insignificant. Yet they ultimately became the origin of all cosmic structure. A story reminding us that sometimes the smallest things create the greatest consequences. Part 8. Quantum fluctuations and the origin of galaxies. At the end of the previous chapter, we paused before an idea that seems almost unbelievable. That during an unimaginably brief moment after the Big Bang, space itself may have undergone a period of expansion so violent that it surpasses all ordinary intuition. Inflation helps explain why the universe today is so vast, so flat, and so remarkably uniform. But then a new question appears, perhaps stranger than all the previous ones. If inflation stretched the infant universe like an enormous fabric, what exactly was stretched along with it? Were there tiny traces already present before space expanded? Fragile differences? The earliest seeds of the future? And here, our story leads us to one of the most beautiful ideas in modern physics. An idea showing that the greatest things sometimes begin with the smallest. So small that they are almost impossible to imagine. Carl Jung once wrote, "Everything that irritates us about others can lead us to an understanding of ourselves." At a very different level, the universe seems to carry a similar lesson. The largest structures we observe today may be traced back to the smallest fluctuations that ever existed. Galaxies stretching across hundreds of thousands of light years, clusters containing thousands of galaxies, cosmic networks of matter spanning hundreds of millions of light years. All of them may have begun from fluctuations smaller than a single atom. Take a moment to let that sink in. Every star in the sky, every planet, every ocean, every living creature, every human being who has ever existed may ultimately be distant descendants of tiny vibrations that appeared during the universe's infancy. In everyday life, we are accustomed to thinking in terms of stability, a calm lake, a quiet room, a space that appears motionless. But when we descend into the quantum world, we discover that perfect stillness scarcely exists. At the smallest scales, reality is always fluctuating, always vibrating, always containing microscopic variations. Quantum fluctuations are part of that strange realm. They are not vibrations in the ordinary sense, not waves upon water, not motions visible to the human eye. Rather, they are tiny variations within the energy fields of the universe, appearing and disappearing, emerging and dissolving, like fleeting ripples across the surface of an invisible ocean. Without inflation, those fluctuations might have remained forever insignificant. They would have left no meaningful trace. But inflation changed everything, like a gigantic magnifying glass. Space expanded so rapidly that those tiny quantum fluctuations were stretched to astronomical scales. Variations that once existed on dimensions smaller than an atom became spread across cosmic distances. Microscopic ripples became slight differences in matter density. Some regions became just a little denser, others became just a little thinner. The differences were extraordinarily small. So small that within the cosmic microwave background they appear only as temperature variations of a few parts in 100,000. Yet those differences became the foundation of the entire story. For gravity is an extraordinarily patient force. It does not need to be powerful. It only needs time. A slightly denser region attracts a little more matter. As it gains matter, it becomes denser still, and then it attracts even more. Millions of years pass, tens of millions, hundreds of millions. The process continues, slowly, steadily, silently, until the first clouds of matter form, then the first stars, then galaxies, then clusters of galaxies, like a tiny seed eventually becoming an entire forest. What always moves me about this story is the contrast between cause and effect. an almost invisible cause, an almost infinite result. Jung often spoke of symbols arising from the unconscious, a small dream, a fleeting image, an emotion that seems insignificant, yet over time, such things can shape an entire psychological journey. In cosmology, quantum fluctuations play a remarkably similar role. What we call cosmic structure today may simply be the mature form of those primordial seeds. If we could observe the universe from a great enough distance, we would see what astronomers call the cosmic web, a magnificent structure. Galaxies are not scattered randomly. They are connected by enormous filaments of matter, forming networks that resemble nervous systems, tree roots, or luminous rivers stretching through space. Between them lie immense voids containing almost no galaxies at all. Along the filaments gather colossal concentrations of matter. Some contain thousands of galaxies. All of this structure, all of this beauty, may be traced back to quantum fluctuations that appeared during the first moments after the Big Bang. This always reminds me of one of the deepest themes in Jung's thought, the idea that potential always precedes form. A seed contains a tree. A dream contains transformation. A symbol contains an entire psychological journey. And the universe appears to operate in a similar way. Tiny fluctuations contain galaxies. Galaxies contain stars. Stars contain elements. Elements contain planets. Planets contain life. And life eventually gives rise to beings capable of looking up at the sky and wondering where they came from. In a very real sense, each of us is the final result of ancient quantum vibrations, not only made of stardust, but also shaped by tiny differences that appeared before the first stars ever existed. And then, as we contemplate this wonder, another question begins to emerge. If quantum fluctuations and inflation could create all the structure of the universe we know, is our universe truly all that exists? Or is it merely a small part of something vastly larger? Could the entire universe we inhabit be only a single bubble within a much greater ocean of reality? An idea so bold that it sounds like science fiction, yet one that arises from the serious equations of modern physics themselves. And that will be the next destination on our journey tonight, the story of bubble universes, and the possibility that our universe may be only one among countless worlds existing somewhere beyond the horizon of human perception. Part 9. The universe may be just a bubble of space. At the end of the previous chapter, we arrived at an idea that feels almost poetic, that all galaxies, stars, planets, and even life itself may have originated from quantum fluctuations smaller than an atom. Fragile vibrations in the childhood of the universe were amplified by inflation and eventually became enormous structures stretching across billions of light years. That alone is strange enough. But science has a peculiar habit. Just when we begin to feel that we understand something, it opens another door, a door leading to even larger questions. And one of those questions is this: what if the entire universe we know is only a small part of a much larger reality? What if what we call the universe is actually just a tiny bubble floating within a far greater ocean? Carl Jung once wrote, "The shoe that fits one person pinches another. There is no recipe for living that suits all cases." Although Jung was speaking about human beings, his words sometimes bring to mind an astonishing possibility in cosmology, that the laws of physics we regard as self-evident may not be the only laws that can exist. Perhaps they are merely the rules governing the region of reality in which we happen to live. And elsewhere, if elsewhere truly exists, those rules might be entirely different. In the previous chapter, we spoke about cosmic inflation. According to some versions of that theory, inflation does not necessarily end everywhere at the same time. It may stop in one region, creating a universe like ours. Yet in other regions, the process continues. Space keeps expanding, keeps generating new regions, keeps creating new bubbles of reality. If this is true, then the universe we inhabit may resemble a bubble rising upon the surface of an ocean. a bubble containing stars, galaxies, planets, thinking beings, but not the only bubble. Imagine standing by the sea on a quiet night. Countless tiny bubbles appear upon the water's surface. Each bubble possesses its own shape, its own size, its own lifespan. Some endure longer, others vanish more quickly. If you lived inside one of those bubbles, you might believe it to be the entire world. Yet, from a broader perspective, it is only a small part of something much larger. Of course, this is merely an analogy. No one knows whether reality truly resembles such a picture. But the image helps us imagine what physicists sometimes call a bubble universe, a concept that sounds like science fiction, yet emerges from equations developed with great seriousness. What makes this hypothesis so fascinating is not only its scale, but also its philosophical implications. If many universes exist, would they resemble ours? Or would each one possess its own set of rules? Today, physicists know that the existence of stars, planets, and life depends upon very specific values: the mass of the electron, the strength of gravity, the speed of light, and many other physical constants. If those numbers were altered even slightly, the universe might have been completely different. Some stars might never have formed. The chemical elements necessary for life might not exist. Matter might never have gathered into galaxies. In some multiverse models, each bubble could possess different values. That means each universe may represent a separate experiment of nature, a place where the rules are arranged slightly differently, a place where light, matter, and time operate in different ways. When I reflect on this, I often think of one of Jung's recurring themes: the diversity of experience. No two human beings are exactly alike. Each person inhabits a unique psychological world. Each views reality through a unique lens. In a certain sense, the multiverse hypothesis carries a similar spirit. It raises the possibility that reality does not have only one version. There may be countless ways for a universe to come into being. Yet this is precisely where we must pause for a moment, because science is not imagination alone. Science also requires evidence, and this is where the story becomes more humble. As of today, there is no direct evidence confirming the existence of bubble universes. No telescope has ever photographed another universe. No radio signal has ever been received from an external reality. No experiment has conclusively demonstrated that the multiverse is real. That does not mean the hypothesis is wrong, but neither does it mean it is correct. For now, it remains at the boundary between theoretical physics and the philosophy of science, a fascinating territory, a place where bold ideas are permitted to exist, yet still await evidence before they can be accepted. Perhaps this is also a beautiful lesson, for in an age of technology and data, it is easy to forget that science is not a collection of final answers. It is an ongoing conversation with the unknown, a journey in which every discovery opens new mysteries. Jung once said, "The more one knows, the more one realizes how much remains unknown." Perhaps nowhere is that more true than in cosmology. For the farther we look, the more we realize that the horizon of our understanding is expanding as well. And then, amid all these reflections about countless possible universes, another question emerges. A more intimate question. Whether there is one universe or many, how can we know anything about them at all? What limits human understanding? Why does there always seem to be a horizon beyond which information cannot pass? To answer that, we must return to a familiar companion, light. For it is the speed of light that creates the most fundamental limits upon our perception of the cosmos. And that will be the next destination on tonight's journey. A story about the speed of light, the limits of information, and the invisible boundaries of human knowledge. Part 10. The speed of light and the limits of knowledge. At the end of the previous chapter, we arrived at one of the strangest territories in scientific imagination, the possibility that our universe is merely a small bubble within a far larger ocean of reality. a captivating possibility, but also a humbling one. For no matter how alluring such ideas may be, we must still confront a very basic truth. Human beings cannot know everything, not because we lack intelligence, not because we lack technology, but because the very structure of the universe imposes certain limits upon knowledge itself. And if there is one silent figure standing behind those limits, it is light. Throughout our journey from the beginning of this story, light has accompanied us. It carries the images of stars, the memories of galaxies, the ancient signals from the childhood of the universe. But tonight, we will look at light in a different way, not merely as a messenger, but as the guardian of the gates of understanding. Carl Jung once wrote, "Knowledge rests not upon truth alone, but upon error also." It is a beautiful idea, for in order to understand what we know, we must first understand what we cannot know. And in cosmology, that boundary begins with the speed of light. Today, most people know that light travels at approximately 300,000 kilometers per second, a number so immense that it is almost impossible to imagine. In a single second, light can circle Earth more than 7 times. In a single minute, it travels a distance that would require commercial aircraft many years to cross. In 8 minutes, it journeys from the Sun to Earth. Within a few hours, it crosses the entire solar system. And despite such astonishing speed, it is still not fast enough to erase the distances of the cosmos. For the universe is larger than anything human intuition was designed to comprehend. But the most important thing is not its speed. It is the role that speed plays. According to our current understanding of physics, light is not merely an optical phenomenon. It is the ultimate limit at which information can travel. No signal, no message, no physical cause can propagate faster than light. This means that everything we know about the world is bound by a very simple rule. We can know only those things whose information has had enough time to reach us. That sounds obvious, yet its consequences are profound. Imagine standing inside an enormous dark room. You possess only a small lantern. The light from that lantern spreads outward at a finite speed. Whatever lies within the illuminated region is what you can know. Whatever lies beyond it does not necessarily fail to exist. You simply have not yet received information about it. The observable universe operates according to the same principle. During the 13.8 billion years since the Big Bang, light has been able to travel only a certain distance. Although space itself has expanded during that time, there remains a limit to what information can bring to us, and that limit creates what astronomers call the observable universe. This leads to a fascinating realization. When we say that the observable universe has a finite size, we are not saying that the entire universe is finite. We are only saying that our knowledge is finite. It is like standing atop a hill and seeing the horizon. The horizon is not the edge of Earth, it is the edge of sight. Likewise, the cosmic horizon is not the edge of existence, it is the edge of information. This always reminds me of a familiar theme in Jungian psychology: consciousness. Jung believed that the portion of ourselves of which we are aware is only a small part of the whole mind. Beneath it lies the personal unconscious, and deeper still, the collective unconscious, a vast ocean far larger than the small portion visible above the surface. In a sense, the observable universe resembles consciousness itself. It is the portion of reality whose information has reached us. Beyond it, there may still exist immense regions we have never seen, and perhaps never will. This leads to an even stranger idea. Every observer possesses a unique observable universe. If you are sitting on Earth, you have a particular observational horizon. If a civilization exists in a galaxy billions of light years away, it too possesses its own observational horizon. Those horizons are not identical. Every location in the universe sees a different portion of reality. This means there is no absolute perspective encompassing the entire cosmos. No one stands outside it all, seeing everything. There is no central seat reserved for a perfect observer. Every being sees from its own position, its own limitations, its own horizon. And this brings us to one of the most revolutionary discoveries of modern astronomy. There is no special central location in the universe. For thousands of years, humanity believed Earth was the center. Then we discovered that we are merely a planet orbiting an ordinary star. Then we discovered that the Sun is only one among hundreds of billions of stars within the Milky Way. Then we learned that the Milky Way itself is only one among hundreds of billions of galaxies. Each step diminished our sense of centrality. Yet at the same time, each step expanded our understanding. Jung often emphasized that psychological maturity begins when the ego stops seeing itself as the center of everything. Cosmology seems to tell the same story. It is not that we become smaller, we become more realistic, not because humanity is less important, but because reality is far larger than we once imagined. And then, amid all these reflections, another question begins to emerge. If light limits what we can know, if the observable horizon limits what we can see, then what happened during the earliest ages of the universe before the first stars appeared? What unfolded during the long era when the universe remained immersed in darkness, a period lasting hundreds of millions of years? No starlight, no mature galaxies, none of the familiar sights we associate with the universe today, only darkness, hydrogen gas, and gravity quietly at work. That will be the next destination on our journey, a chapter called The Cosmic Dark Ages. Part 11, The Cosmic Dark Ages. At the end of the previous chapter, we explored a truth that is both humbling and profound, that all of our knowledge is limited by the speed of light. We can know only what information has had time to bring to us. We can see only what light has had enough time to tell us. And because of this, the observable universe is not the entirety of reality. It is merely the portion of reality that has had time to converse with us. Yet as we follow those ancient rays of light backward into the past, we arrive at a very special era, a place in time where light seems to disappear from the story, a place without luminous galaxies, without constellations, without the rivers of light stretching between clusters of galaxies. Only darkness, a darkness that lasted for hundreds of millions of years. Astronomers call this period the Cosmic Dark Ages. At first hearing that name, many people imagine something frightening, as though the universe had entered a barren and lifeless age. But in truth, this is not a story about an ending. It is a story about preparation, not about death, but about gestation. Carl Jung once wrote, "One does not become enlightened by imagining figures of light, but by making the darkness conscious." Perhaps no quotation is more fitting for this chapter, for the Cosmic Dark Ages were not an empty void without meaning. They were a necessary part of the story, a pause before the symphony begins, a long night before dawn. To understand this, let us return to the moment after the cosmic microwave background was born. Roughly 380,000 years after the Big Bang. By then, the universe had cooled enough for electrons and protons to combine. The first hydrogen atoms appeared. Light was released. Space became transparent. That was the moment that created the CMB we discussed earlier. But after that ancient light was emitted, what happened next? Surprisingly, not very much, at least not in the way we usually imagine. There were no cosmic fireworks, no galaxies blazing into existence overnight, no star systems stretching across the sky. The universe at that time was far simpler. It contained almost nothing except two elements, hydrogen and helium, the lightest elements in nature, floating through space like endless clouds of mist. If it had somehow been possible to observe the universe, then with human eyes, which of course it was not, we would have seen a realm that was almost completely dark, not because matter was absent, but because sources of light had not yet appeared. No stars had been born, no suns illuminated the darkness, no cosmic lighthouses that we now call galaxies. Only gas. Gas everywhere, an immense ocean of hydrogen and helium stretching seemingly without end. This always reminds me of an image from Jungian psychology. a period in which an idea has not yet taken form, a time when an inner transformation is underway but cannot yet be seen. From the outside, nothing appears to be changing. Yet, beneath the surface, the most important processes are quietly unfolding. The universe during the Dark Ages was much the same. On the surface, there was silence, but beneath that silence, a force was working ceaselessly. Gravity. Perhaps gravity is the most patient force in all of nature. It is not loud, it does not explode, it does not put on dramatic displays. It simply pulls, gently, continuously, never growing tired. Throughout the Dark Ages, gravity began its work. Regions of matter that were ever so slightly denser, the tiny differences we discussed in the chapter on quantum fluctuations, began attracting additional gas from their surroundings. As they gathered more gas, they became heavier. As they became heavier, they pulled more strongly. The process continued, little by little, million years by million years, like tiny snowflakes gradually accumulating into a great snowball rolling down a mountainside. No one could have watched the process with the naked eye. It was too slow, too quiet, yet it was preparing the birth of the first galaxies. What is remarkable is that the most important things in the universe often happen in exactly this way, without noise, without spectacle. A star is born from millions of years of accumulated matter. A planet forms through countless small collisions. A galaxy grows through billions of stars. A human being matures through innumerable experiences that seem insignificant at the time. Jung often emphasized that the deepest transformations of the soul rarely occur in a single dramatic moment. They are the result of slow changes unfolding within the darkness of the unconscious. The universe appears to follow a similar principle. The Dark Ages were not a wasted period. They were a preparation, the winter before spring, the seed before the forest, the sleep before awakening. If we look across the 13 billion, 8 billion year history of the universe, we can recognize a beautiful pattern. Periods of silence often precede the greatest turning points. Before the first stars ignited, before the first galaxies formed, before light returned, there was an age of darkness, not the darkness of despair, but the darkness of potential, a darkness that contained the future within it. And that always makes me think about our own lives. There are times when it seems that nothing is happening, quiet seasons, periods of waiting, pauses that we are often tempted to dismiss as meaningless. Yet sometimes, it is precisely within those silences that the deepest transformations are taking place. Just like gravity during the Dark Ages, no one could see it, yet the entire future of the universe was being prepared. And then, after hundreds of millions of years of patience, after hundreds of millions of years of gathering, after hundreds of millions of years of darkness, something extraordinary finally happened. Somewhere within the first clouds of hydrogen, matter became dense enough, temperatures rose, pressure increased, and the first nuclear furnaces burst into life. The first stars were born. Light returned to the universe. The first dawn of the cosmos began to emerge. And that will be the next destination on our journey tonight. The story of the first stars, the ancient fires that illuminated the primordial darkness, and that forged the elements required for every planet, every ocean, and every form of life that would one day follow. Part 12. The First Stars. At the end of the previous chapter, we traveled through one of the quietest eras in the history of the universe, an age lasting hundreds of millions of years. No dawn, no brilliant galaxies, no cosmic lighthouses of the kind we see in the night sky today. Only hydrogen, helium, and gravity quietly doing its work. Like a patient gardener planting seeds in darkness. No one could see it, no one could hear it. Yet the future was being prepared. Then at last, after hundreds of millions of years of waiting, the thing the universe had been silently preparing finally arrived. The first stars were born. A first light appeared within the ocean of primordial darkness. A first dawn began spreading through space. Carl Jung once wrote, "The creation of something new is not accomplished by the intellect, but by the play instinct acting from inner necessity." Whenever I read those words, I think of the first stars, for their appearance was not an accident, not a random miracle, but the inevitable result of forces that had been quietly at work for a very long time. Within the immense clouds of hydrogen and helium that filled the dark ages, gravity continued drawing matter together. The gas began to gather, denser, hotter, heavier. Little by little, millions of years passed. The clouds became so dense that their own weight began compressing matter toward the center. Temperatures increased, pressures increased, until a special threshold was crossed. A threshold that changed the entire history of the universe. Nuclear fusion began. Hydrogen was transformed into helium. Enormous amounts of energy were released, and the first star ignited. This was the first moment since the Big Bang that the universe possessed genuine sources of light of its own. No longer merely the fading glow left behind from the past, but new light. Light created in the living present of the universe itself. If it had been possible to witness that moment, which no one could, it might have appeared almost sacred. Across an endless ocean of darkness, the first points of light began to emerge, like candles being lit inside a vast room. Like humanity's first campfires glowing within a primordial night. Yet strangely, those first stars were not like the familiar stars we know today. Astronomers believe they may have been far larger than our Sunday, perhaps dozens of times more massive, perhaps even hundreds of times more massive. They are known as population 3 stars, the third population according to modern classification, yet in reality, the very first generation of stars in cosmic history. Why were they so large? Because the universe at that time consisted almost entirely of hydrogen and helium. The heavier elements that help gas cool efficiently did not yet exist. As a result, clouds of matter had difficulty fragmenting into smaller pieces. Instead, they collapsed into enormous structures. The first stars therefore became giants. But as with many things in life, great size often comes with a shorter lifespan. These colossal stars burned fiercely. They consumed their fuel at astonishing rates. They did not survive for billions of years like our Sunday. Some may have existed for only a few million years, a mere blink of an eye on the cosmic timescale. This always reminds me of a paradox Jung often returned to, that sometimes the shortest-lived things leave the longest-lasting influence. A dream, an encounter, a moment of realization, a profound experience. It may last only minutes, yet its imprint can remain with us for a lifetime. The first stars were much the same. Their lives were brief, yet their legacy remains present within every living body on Earth today. For before those stars appeared, the universe contained almost nothing beyond hydrogen and helium. No carbon, no oxygen, no silicon, no iron, no calcium, no phosphorus, none of the elements necessary for rocks, water, and life. The early universe was simple, too simple to create a planet like Earth, too simple to create forests, oceans, or thinking beings. But within the cores of those first stars, that began to change. Fusion reactions did not stop with helium. When stars were sufficiently massive, they continued producing heavier elements: carbon, oxygen, neon, magnesium, silicon, and eventually iron. Each new element created was like a new chapter in the chemical story of the universe. A new possibility, a new future, a new form of complexity. If hydrogen was the universe's first alphabet, then stars were the first writers to learn how to arrange those letters into richer and more meaningful words. Yet the greatest wonder was still to come, for those elements could not help create planets if they remained imprisoned inside stars forever. They had to be released. They had to be given back to the universe. And for that to happen, the first stars had to die. That may sound sad, but in astronomy, death is often an act of creation. When massive stars reach the end of their lives, they explode in brilliant supernovae. supernovae, among the most violent events nature has ever produced. In those moments, the elements are hurled into space. Carbon is released, oxygen is released, silicon is released, iron is released. The materials that will become rocks, the materials that will become oceans, the materials that will become living bodies. Jung once said, "There is no coming to consciousness without pain. There is no awakening without passing through suffering." In a certain sense, those words also fit the history of the universe. For in order to create life, the first stars had to undergo destruction. For the next generation to appear, the first generation had to end. For planets to exist, stars had to die. It is a law that is both sad and beautiful. A law revealing that creation and ending are not opposites. They are often two aspects of the same process. And so, as the heavy elements began spreading throughout space, the universe entered an entirely new chapter. Those first flames did not merely bring light. They began transforming the very environment around them. Their radiation affected the ancient hydrogen gas. The primordial darkness slowly retreated. A new age was preparing to begin. An age in which bubbles of light would spread throughout the young universe. And that will be the next destination on our journey tonight. The story of reionization, the true dawn of the universe, when the first stars did not merely illuminate space, but awakened an entire cosmos that had slept in darkness for hundreds of millions of years. Part 13. Reionization, the dawn of the universe. At the end of the previous chapter, we witnessed the birth of the first stars. Ancient fires ignited amid an ocean of darkness that had lasted for hundreds of millions of years. They were born from primordial hydrogen and helium. They lived brief lives. They burned brilliantly. And when their lives came to an end, they gifted the universe its first elements necessary for planets, oceans, and life itself. But the wonder of the first stars was not only found in what they created within their cores, it was also found in what their light did to the universe around them. For when the first stars burst into existence, they did more than push back the darkness. They began transforming the very structure of space itself. And from that moment, a new chapter in cosmic history began. A chapter astronomers call the epoch of reionization, the era of reionization, or, in a more poetic sense, the dawn of the universe. Carl Jung once wrote, "Who looks outside, dreams. Who looks inside, awakes." I often think that these words take on a special beauty when placed alongside the story of reionization. For after hundreds of millions of years immersed in darkness, it almost seems as though the universe itself was awakening, not with sound, not with explosions, but with light, a slow awakening, quiet, spreading from the smallest point of illumination across the vastness of space. To understand this, let us remember the state of the universe after the Dark Ages began. Neutral hydrogen was everywhere. Hydrogen atoms filled nearly all of space. They were like a thin mist stretching throughout the young universe. Light could pass through them at many wavelengths. But for energetic ultraviolet radiation, hydrogen acted as a barrier, a curtain, a veil, a haze that prevented space from becoming truly transparent. Then the first stars appeared. Those gigantic nuclear furnaces emitted enormous amounts of ultraviolet radiation. High-energy photons began striking the surrounding hydrogen atoms. When an ultraviolet photon is energetic enough to collide with a hydrogen atom, it can knock the electron free. Neutral hydrogen becomes ionized hydrogen. A simple process from the perspective of physics, yet one with enormous consequences for the history of the universe. Because from that moment forward, light began altering the very environment through which it traveled. This always reminds me of a familiar idea in Jungian psychology. Consciousness does not merely observe the inner world, it transforms the inner world. When something is brought from the darkness of the unconscious into the light of awareness, the very act of becoming conscious changes it. The light of the first stars seems to have done something similar to the universe itself. They did not merely illuminate space, they changed space. At first, the process was highly local. Each star created a small, ionized region around itself, like a candle lit within a foggy night. Around that flame, darkness retreated. But farther away, the night remained unchanged. If we could have viewed the universe from an immense distance at that time, we would have witnessed a strange sight. Not a completely bright universe, nor a completely dark one, but countless small bubbles of light emerging within an ocean of darkness. Each star, each young galaxy, created its own bubble, a region of space where hydrogen had been ionized, an island of light within the primordial sea of night. And then time continued to flow. More stars appeared, more galaxies formed, more sources of light were born. The bubbles of light began to expand. They grew larger, reached farther, collided with one another, connected with one another, merged together, like ripples on the surface of a lake, when many raindrops fall at once, at first separate, then overlapping, finally becoming one. There is something profoundly beautiful about that image, for this is not the story of a single light overcoming darkness. It is the story of countless small lights changing an entire universe together. Jung often emphasized that profound transformation rarely comes from a single moment. It comes from countless small changes accumulated over time. A small realization, a small experience, a small understanding, eventually creating the maturity of an entire human being. The universe seems to work in much the same way. No single star illuminated all the darkness by itself, but millions, billions of sources of light together accomplished exactly that. Hundreds of millions of years passed. The ionized regions continued expanding. More and more neutral hydrogen was transformed. More and more space became transparent to ultraviolet light, until a special moment arrived. A moment astronomers regard as the end of the epoch of reionization, when most of the hydrogen between galaxies had become ionized, when the final curtains of the dark ages were drawn aside, when light could travel more freely through cosmic space. That was the true dawn of the universe. Not the dawn of a planet, not the dawn of a star, but the dawn of the entire observable universe. If the Dark Ages were the universe's long winter, then reionization was its spring, the moment when seeds planted long before finally began to bloom, the moment when light ceased to be isolated points of fire and became a fundamental feature of the cosmos itself. What moves me most about this story is nature's patience. Nothing happened in a hurry. There was no sudden leap. The journey from darkness to light lasted hundreds of millions of years, a journey so slow that within a human lifetime, it would seem as though nothing had changed at all. Yet on the timescale of the universe, it was a magnificent transformation. Perhaps there is a gentle lesson for us here as well. For sometimes the deepest changes in life happen in exactly the same way, not in a day, not in a week, but through small steps that are almost impossible to notice, until one day we look back and realize that we have entered a new dawn. And then, as light spread throughout space, the first galaxies continued to mature. New generations of stars appeared. Increasingly complex structures formed. The universe began to resemble the picture familiar to us today. Yet many mysteries still lay ahead. How can we see the most ancient galaxies from that era? How can humanity observe light that began its journey more than 13 billion years ago? To answer that question, we must meet one of the most extraordinary tools ever created by human beings. A telescope positioned more than 1 million kilometers from Earth. A machine designed to look back into the childhood of the universe. And that will be the next destination on our journey tonight. The story of the James Webb Space Telescope. Humanity's new eyes turn toward the most distant dawns of time. Part 15. The True Shape of the Universe. At the end of the previous chapter, we journeyed alongside the James Webb Space Telescope, a machine created to see farther than any eyes in human history. Thanks to Webb, we have observed galaxies so ancient that their light began its journey when the universe was still very young. Those images did more than expand our knowledge. They awakened a larger question, a question that has followed humanity since the first nights when our ancestors gazed up at a sky filled with stars. If we continue farther still, beyond the galaxies, beyond the galaxy clusters, beyond the immense cosmic webs woven throughout space, what would we eventually encounter? Would there be a final edge to the universe? An invisible wall? A boundary where everything comes to an end? Or has the question itself been mistaken from the beginning? Carl Jung once wrote, "The greatest and most important problems of life are all fundamentally insoluble." It is a deeply humble statement, and perhaps nowhere is it more appropriate than when we speak about the shape of the universe itself. For this is one of the greatest questions science has ever faced. A question so simple that a child can ask it, yet so profound that the greatest minds have still not answered it conclusively. What is the true shape of the universe? When people hear that question, they often imagine an object, something shaped like a sphere, or a box, or some gigantic cosmic structure. But reality is far more complicated, because the universe is not inside space. The universe is space, and that is where our ordinary intuition begins to struggle. Everyday experience teaches us that everything exists inside something larger. A room exists inside a house. A house exists inside a city. A city exists on Earth. Earth exists within the solar system. We are accustomed to asking, where is this located? But when we speak about the entire universe, that question becomes strange, because if the universe includes all space, then it does not exist inside some larger space that we know about. This is why physicists sometimes say that the question, where is the universe, may not have physical meaning. The same is true of the question about the edge of the universe. Does a final boundary exist? A place beyond which there is nothing? Today, science considers several major possibilities. The first possibility is the one that overwhelms the imagination the most. The universe may be infinite, without an endpoint, without borders, without an edge, without any place where one could say, this is where it ends. If this is true, then no matter how far you travel, there will always be more space ahead. Beyond galaxies, beyond galaxy clusters, beyond anything observable, space simply continues, without interruption, without conclusion. When I think about that possibility, I often experience a very unusual feeling, not exactly fear, not entirely awe, but a kind of profound humility. For the human mind was shaped within a finite world. We can imagine 1,000,000, 1,000,000,000, even 1,000,000,000,000. But infinity is something altogether different. Not merely a very large number, but something without an ending. Jung spent much of his life studying symbols that appear within the human psyche. He noticed that across cultures, people created images meant to express the infinite. Circles, mandalas, symbols of wholeness. Perhaps because deep within ourselves, our minds are always trying to approach what lies beyond imagination. And an infinite universe may be one of those things. But there is another possibility, a possibility that sounds even more paradoxical. The universe may be finite, yet without boundaries. At first, this seems impossible. How can something be finite and still have no edge? Imagine that you are a two-dimensional creature living on the surface of Earth. You cannot look upward or downward. You can only move along the surface. If you begin traveling in one direction and continue forever, you will never encounter the edge of the world. There is no wall, no cliff, no endpoint. Eventually, you return to where you started. Earth's surface is finite, yet it has no boundary. Some cosmological models suggest that all of space may operate according to a similar principle, but in higher dimensions. This would mean that the universe could have a finite volume, yet you would never find its edge, because quite simply, no edge exists. This idea always reminds me of the psychological journey Jung called individuation. the process through which a person seeks their true self. At first, we imagine there will be a final destination, a final answer, a state of complete fulfillment. But the deeper we travel into that journey, the more we realize there is no ultimate edge to understanding. Each discovery leads to another. Each horizon reveals a new horizon. And then there is a third possibility, one even stranger than the others. The universe may be wrapped around itself. Certain mathematical models allow space to possess a structure in which, if you travel straight long enough in one direction, you eventually return to your starting point. Not because you change direction, but because the structure of space itself brings you back. Like a character in a video game who exits the right side of the screen and reappears on the left. The idea sounds like science fiction, yet mathematically, it is entirely possible. Of course, we currently have no evidence that the universe actually behaves this way, but the mere existence of such possibilities reveals just how strange reality may truly be. What fascinates me most is that regardless of which model we choose, an infinite universe, a finite universe without boundaries, or a wrapped universe, they all lead to the same conclusion. The universe is unlike any familiar object in our daily lives. It exists far beyond the images our intuition evolved to understand. And perhaps that is the most beautiful part. For every time science expands our vision, it simultaneously expands the mystery. Every answer gives birth to new questions. Every discovery carries us toward another horizon. And then, as we contemplate the shape of space, another question begins to emerge from the distance. Even if we knew the shape of the universe, what determines its destiny? What causes galaxies to move farther and farther apart? What is silently stretching the very fabric of space? A mysterious force that we still do not truly understand. Something invisible, yet seemingly controlling the future of the entire cosmos. And that will be the next destination on our journey tonight. The story of dark energy, one of the greatest mysteries modern science has ever faced. Part 16, Dark Energy. At the end of the previous chapter, we stood before one of humanity's oldest questions. What is the true shape of the universe? Does space stretch endlessly? Is it finite yet without boundaries? Or is its structure stranger than anything human intuition can imagine? But as astronomers attempted to answer those questions, they unexpectedly uncovered another mystery, an even larger one. A mystery concerning not only the shape of the universe, but its ultimate fate. For it turns out that space is not merely expanding, it is expanding faster and faster. And that realization feels like a story in which, halfway through the final chapter, the characters suddenly discover that the rules they trusted from the beginning may not tell the whole truth. Carl Jung once wrote, "The pendulum of the mind oscillates between sense and nonsense, not between right and wrong." The history of dark energy carries a similar feeling. At first, it seemed absurd, something no one expected. Yet the more scientists studied it, the more they realized that this seemingly absurd thing might be shaping almost the entire future of the universe. To understand why this discovery was so shocking, let us return to the early 20th century. After the discovery that the universe was expanding, most scientists believed something very reasonable. If galaxies were moving apart, then gravity must be trying to pull them back together. Like a ball thrown into the sky, it continues upward, but gravity is always pulling it downward. The question was simply, would gravity eventually be strong enough to slow the expansion and pull everything back together? For many decades, this was the widely accepted picture. The universe might expand forever, or one day its expansion might slow. But in either case, gravity was assumed to be acting as a brake. Then came the late 1990s. A series of observations involving distant supernovae revealed a surprise. Astronomers discovered that distant galaxies were not merely moving away from us, they were moving away faster than expected. Space was not slowing down, it was accelerating. Imagine throwing a ball into the air. You wait for it to slow down, but instead of slowing, It begins moving faster and faster. You would naturally conclude that some invisible force must be pushing it. That is exactly how the astronomical community felt. Something was influencing the entire universe. Something powerful enough to oppose the gravity of every galaxy, every star, and every cluster of galaxies. Something we had never recognized before. And because nobody knew what it was, scientists gave it a simple name: dark energy. The name sounds mysterious, but the word dark here does not mean black or sinister. It simply means unknown. A name that serves as an honest admission from science. We can see its effects, but we do not yet understand its nature. There is something deeply Jungian about that naming. Jung always emphasized that maturity begins by acknowledging what we do not know, not by pretending we understand everything. In his psychology, the unknown appears as the shadow of the unconscious. In cosmology, the unknown appears as dark energy, an invisible presence with immense influence. What makes dark energy so strange is that we cannot see it. We cannot touch it. We cannot collect it in a laboratory. It emits no light, reflects no light, leaves behind no direct traces that our senses can perceive. The only thing we observe is its effect, like seeing leaves move without seeing the wind, like seeing ripples on a lake without seeing the stone that caused them. The universe is accelerating in its expansion. That is the footprint of dark energy. But what exactly is dark energy? Even today, it remains one of the greatest questions in modern physics. Some hypotheses suggest that it may be the energy of empty space itself. The idea sounds extremely strange. When we think about empty space, we usually imagine nothingness, an absolute void. But quantum physics suggests that the vacuum is not truly empty. Even within the emptiest regions of space, quantum fluctuations continually appear. Virtual particles emerge and disappear. Microscopic vibrations never cease. Perhaps that energy is what causes space to expand more rapidly. But today, we still do not know for certain. And perhaps that is the most fascinating part. After thousands of years of watching the sky, after centuries of modern physics, after building the most powerful telescopes ever created, we still do not know what most of the universe actually is. According to current estimates, ordinary matter, the material that forms stars, planets, trees, oceans, and human bodies, accounts for only a small fraction of the universe. The rest belongs to dark matter and dark energy, things we are only beginning to understand. Whenever I reflect on that fact, I often remember another statement from Jung: until you make the unconscious conscious, it will direct your life, and you will call it fate. Perhaps dark energy resembles a kind of cosmic unconscious, something silently influencing everything, shaping the future of space itself, yet remaining beyond our understanding. And because dark energy governs the rate at which the universe expands, it is also helping determine the ultimate future of every galaxy, every star, every planet. Even the people listening to this story, if dark energy continues to dominate, galaxies will drift farther and farther apart. The space between them will continue to grow. The skies of future civilizations may become far lonelier than the skies we look upon today. But before we explore that distant future, we must first understand another mysterious character, a presence nearly as elusive as dark energy, something that emits no light, reflects no light, yet provides the gravitational framework upon which galaxies are built, something that appears to exist throughout the universe. And that will be the next destination on our journey tonight. The story of dark matter, the invisible architect behind the largest structures in the cosmos. Part 17, Dark Matter. At the end of the previous chapter, we encountered one of the greatest mysteries of modern science: dark energy, an invisible presence that appears to be driving the accelerated expansion of the universe. We cannot see it, we cannot touch it, we cannot directly measure its true nature, yet we can see its footprints on the scale of the entire cosmos. That alone might seem mysterious enough, but the universe always finds ways to surprise us. For alongside dark energy, there exists another enigmatic character, quieter, closer to home, and in some ways, just as important. Something that emits no light, reflects no light, cannot be seen through any ordinary telescope, yet somehow holds galaxies together. Scientists call it dark matter. Carl Jung once wrote, "One does not become enlightened by imagining figures of light, but by making the darkness conscious." Perhaps that statement has never been more fitting than when discussing dark matter, for much of what shapes the structure of the universe does not lie within the light. It lies within the unseen. For most of human history, we have been accustomed to trusting what we can see: the stars in the sky, the glowing clouds of gas, the magnificent spiral galaxies. Together they form the familiar picture of the universe. But during the 20th century, astronomers began noticing something strange. Galaxies appeared to be behaving incorrectly, at least according to what physics predicted. Imagine a carousel in a park. The horses near the center move more slowly than those farther out. That is what intuition expects. The same is true in our solar system. Planets farther from the sun move more slowly than planets that orbit closer. But when astronomers measured the rotational speeds of stars inside galaxies, they discovered something unexpected. Stars near the edges of galaxies were not slowing down as predicted. They were moving much faster, so fast that they should have been flung out of their galaxies long ago. And yet they remained, still orbiting, still bound together as stable systems. It was as though you spun an umbrella and found that the water droplets at the outer edge refused to fly away, despite moving far too quickly. Something was holding them in place, some additional gravitational force, some source of mass that we could not see. At first, many researchers suspected that perhaps we had simply overlooked some stars or dark clouds of gas. But the more observations accumulated, the larger the problem became. The visible mass simply was not enough. Gradually, a bold possibility emerged. Perhaps most of the matter in the universe is completely invisible. It does not emit light. It does not reflect light. It does not interact with light in the way ordinary matter does. Yet it still possesses mass. It still generates gravity. It still influences everything around it. At first, the idea sounded bizarre, but evidence began appearing everywhere, not only in individual galaxies, but in enormous galaxy clusters, in the way gravity bends light, in the formation of large-scale cosmic structures. Every clue pointed toward the same conclusion. There is more matter than we can see, much more. Today, estimates suggest that ordinary matter, the atoms that make up stars, planets, oceans, forests, and human bodies, accounts for only a small fraction of the universe's total matter content. Most of the rest is dark matter. That means everything familiar to us. Every mountain, every ocean, every living creature, every civilization is merely a thin layer floating on the surface of a vastly larger ocean of invisible matter. When I think about this, I'm often reminded of the central ideas in Jungian psychology. Jung believed that the conscious mind is only a small part of the psyche. Beneath it lies the personal unconscious, and deeper still, the collective unconscious, invisible layers that nevertheless exert enormous influence over our thoughts and behavior. Dark matter brings that image to mind, not because they are scientifically related, but because both remind us of the same lesson, that what is invisible can sometimes be more important than what is visible, that what we cannot see may still shape everything we can. Even more remarkably, dark matter does not merely hold galaxies together. It also appears to have provided the original framework for their formation. In the early universe, dark matter began clustering under the influence of gravity. It formed immense networks stretching across space. Astronomers often call this structure the cosmic web. Along these invisible filaments, hydrogen and helium gas began to gather. Stars formed. Galaxies emerged. Galaxy clusters grew. In a sense, dark matter is like the steel framework inside a skyscraper. You do not see it from the outside, yet the entire structure depends upon it. Without the framework, the building could not stand. Without dark matter, the universe might have looked entirely different. Galaxies might not have formed as they did. Stars might have been distributed differently. Life itself may never have emerged. What is astonishing is that despite being everywhere, we still do not know exactly what dark matter is. There are many hypotheses. Perhaps it is a new kind of particle never before detected. Perhaps it is a form of matter entirely different from anything familiar. Perhaps it is connected to deeper aspects of physics that we have yet to understand. Laboratories around the world are searching for it. Telescopes are hunting for its traces. Yet so far, dark matter has kept its secret, and perhaps that makes the story even more beautiful, because it reminds us that the universe remains filled with mysteries. After centuries of science, after space probes, after the most powerful telescopes ever built, we are still living among unknowns. Jung once said, "The more one knows, the more one realizes how much remains unknown." Dark matter may be the perfect embodiment of that statement. We know it exists. We observe its influence, yet its true nature remains beyond our grasp. And as we contemplate these invisible ingredients shaping the cosmos, another question begins to emerge. If dark matter provides the framework for galaxies, if dark energy governs the expansion of space, then where exactly are the ultimate boundaries of what we can observe? Are there regions of the universe whose light has never reached us? Are there galaxies that still exist, yet with which we can never communicate? That will be the next destination on our journey tonight. A story about the invisible horizons of the universe, the ultimate boundaries of light, information, and human knowledge. Part 18. The different cosmic horizons. At the end of the previous chapter, we met one of the most mysterious characters in the universe, dark matter, an invisible substance that neither emits nor reflects light, yet provides the gravitational framework for galaxies and galaxy clusters. It is everywhere. It influences every large-scale structure in the cosmos. And yet it continues to evade every attempt at direct observation. Naturally, this leads us to a question. If there are things that exist which we cannot see, could there also be regions of the universe that we will never see? Places forever beyond the reach of any telescope? Limits imposed not by technology, but by the very nature of space and time? To answer those questions, we must explore a concept that is both scientific and profoundly philosophical. The cosmic horizon. Carl Jung once wrote, "We cannot change anything until we accept it." Perhaps the same is true in science. Part of intellectual maturity is accepting that knowledge has limits. Not every door can be opened. Not every distance can be crossed. Not every mystery can be solved. And the cosmic horizon is perhaps the clearest symbol of that truth. When people hear the word horizon, they often think of the line where the sky meets the ground. Yet we know that line is only an illusion of perspective. If you move toward it, it retreats farther away. In cosmology, the idea is similar. A horizon is not a wall, not a physical boundary, not the place where the universe ends. It is the limit of information, the boundary of what light has had time to bring to us. The first type is called the particle horizon. The name sounds complicated, but the idea behind it is simple. The universe is about 13.8 billion years old. Light travels at a finite speed. Therefore, only signals that have had enough time to reach us can be observed. If a source is too distant, its light simply has not arrived yet, not because it does not exist, but because the information is still on its way. Imagine standing on a hill at night. Far away in the darkness are countless lamps, yet you can only see the lamps whose light has reached your eyes. The others may still exist. Their light simply has not arrived yet. The particle horizon is the boundary of everything whose light has had time to reach us since the beginning of the universe. It marks the limit of the observable universe, not the limit of existence, but the limit of awareness. This always reminds me of one of Jung's most familiar themes, the unconscious. Jung believed that consciousness is merely a small island floating upon a vast ocean of mind. What we know is only the portion illuminated by awareness. Beyond that lie unexplored territories, regions that are not non-existent, only unknown. The particle horizon is much the same. It is the boundary of light, the boundary of what has become known. But the universe contains another horizon, one even stranger, and perhaps more melancholic, the event horizon of the universe. If the particle horizon is about the past, the event horizon is about the future. It answers a different question. Not what can send information to us, but what will still be able to communicate with us in the future. This is where the story becomes especially remarkable. The dark energy we discussed earlier is causing the universe to expand faster and faster. Galaxies are not merely drifting apart, they are separating at an ever-increasing rate, so rapidly that there are regions of space whose light emitted today will never reach us. Not because light is too slow, but because the space between us and the source is expanding too quickly. Imagine swimming upstream in a river. If you swim faster than the current, you move forward. But if the current is stronger than your swimming speed, you are carried backward. Light faces a similar situation on cosmic scales. There are regions where the expansion of space outpaces the ability of light to overcome the growing distance. What is astonishing is that some galaxies are still visible to us today. Their ancient light is still arriving at Earth. Yet any new signal they emit at this very moment will never reach us. Never, for all eternity. It is an idea that often inspires quiet reflection. A galaxy may still be present in the sky, yet forever beyond the possibility of communication, like receiving old letters from a distant friend. You can still read letters they sent years ago, but every new letter will never arrive. There is something deeply human in that image, and deeply Jungian. Jung often wrote about limits that cannot be overcome in human life. Not every meeting lasts forever. Not every connection endures eternally. Some things remain present in memory, yet no longer belong to our future. Galaxies beyond the cosmic event horizon are much the same. They remain present in the light we receive today, but their future and ours have already begun to separate. That is what makes the cosmic event horizon one of the most moving concepts in cosmology, because it is not merely about distance, it is about connection, about the ultimate limits of communication, about boundaries that even light cannot cross. And as we reflect on those horizons, an even larger question begins to emerge. If there are regions beyond observation, if there are galaxies forever beyond communication, could the universe we know be only a tiny part of a much larger reality? Could countless other worlds exist beyond the observable horizon? Could there be more than one universe? That will be the next destination on our journey tonight. A story that stands at the frontier of modern science, while touching the deepest limits of human imagination. The story of the multiverse. Part 19. The multiverse. At the end of the previous chapter, we stood before the invisible horizons of the universe. Not walls, not physical boundaries, but limits of information, limits that even light itself cannot cross. We spoke of the particle horizon, the boundary of everything whose light has had enough time to reach us, and the event horizon, the boundary of everything that will still be able to communicate with us in the future. But when we contemplate those horizons, a natural question begins to arise. If there are regions beyond the observable horizon that we cannot see, do those regions continue forever? Or somewhere farther beyond, might there exist entirely different universes, different realities, different laws, different possibilities? Carl Jung once wrote, "The world hangs on a thin thread, and that is the psyche of man." I often think of this quote when reflecting upon the boldest ideas in science, because every journey of discovery begins in a very small place. A question, a curiosity, a feeling that reality may be larger than what we can presently see, and perhaps no idea in modern cosmology, embodies that feeling more than the multiverse. Even the name itself feels dreamlike. Not one universe, but many universes. Not one reality, but countless realities existing side by side. It sounds like science fiction, yet what is fascinating is that the idea did not emerge from novels. It emerged from serious physics, from attempts to understand how our own universe came into existence. Earlier, we discussed cosmic inflation, that brief instant after the Big Bang when space may have expanded at an almost unimaginable rate. Inflation explains many things. Why the universe appears flat, why its temperature is nearly uniform in every direction, why large-scale structures could form. But as physicists explored the theory more deeply, a strange possibility emerged. What if inflation did not end everywhere at the same time? What if in some regions it stopped and created a universe like ours, while in other regions it continued? If that is true, space may resemble an ocean, continually producing new bubbles. Each bubble would be its own universe, its own reality, its own history, its own set of physical laws. This idea is often called eternal inflation. Imagine a pot of boiling water. Bubbles continually form throughout the liquid. Each bubble possesses its own boundary, its own interior, its own history. In this metaphor, our universe might be only one bubble among countless others, a tiny bubble floating within a much larger ocean of reality. What makes this idea extraordinary is not merely the number of universes. It is the possibility that each universe may be different, very different. Today, physicists understand that the existence of stars, planets, and life depends upon very specific values: the mass of the electron, the strength of gravity, the charge of the proton, the speed of light. These physical constants are like musical notes, composing the symphony of the cosmos. Change them slightly, and the entire melody may become something else. Some hypothetical universes might never produce stars. Some may never form stable atoms. Some might exist only briefly before collapsing. Others might contain forms of structure beyond anything our imagination has conceived. This always reminds me of one of Jung's favorite themes, the infinite diversity of human experience. Jung recognized that every soul is its own world. Every individual is a unique psychological universe. Even while sharing the same planet, no two people experience reality in exactly the same way. In a sense, the multiverse hypothesis extends that idea onto a cosmic scale. Not merely many perspectives, but many realities. Not merely many stories, but many versions of the rules that create stories. Yet this is also where we must pause, because science is not built upon imagination alone. It is built upon evidence, and every serious discussion of the multiverse must acknowledge one important fact. At present, we possess no direct evidence that other universes actually exist. No telescope has observed another universe. No signal has been confirmed from beyond our observable cosmos. No experiment has conclusively demonstrated that the multiverse is real. That is why the idea occupies a unique territory between theoretical physics, philosophy of science, and imagination. It is not science fiction, but neither is it an established fact. It is a possibility, a hypothesis, a doorway standing slightly open, and perhaps that makes it even more beautiful, because sometimes the value of an idea does not lie in whether it has been proven, but in its ability to expand the horizon of thought. Jung once said, "The least of things with a meaning is worth more in life than the greatest of things without it." The multiverse may be true, it may be false, but it reminds us that reality could be far larger than our everyday intuition allows us to imagine. It reminds us that science is not merely the collection of answers, it is also the art of asking questions large enough to matter. And as we contemplate those endless possibilities, one final question begins to emerge. If countless universes truly exist, if other realities truly lie beyond our own, would that change the ultimate fate of the universe we inhabit? What will happen to galaxies in the distant future? What will happen when the final stars fade away? What will happen when the cosmic symphony approaches its final notes? That will be the final destination of our journey tonight. A story no longer about origins, no longer about the past, but about the farthest future imaginable, the story of the ultimate fate of the universe. Part 20. The far future of the universe. At the end of the previous chapter, we stood before one of the boldest ideas ever imagined by the human mind, the multiverse. The possibility that our universe may be only a small island within a much larger ocean of reality. A possibility that still occupies the borderland between science, philosophy, and imagination. But tonight, before we conclude our journey to the edge of the universe, we return to a more intimate question. Not how many universes may exist, but what will happen to the universe we call home? What awaits all galaxies, all stars, all planets, and every story ever told within this immense expanse of space? Carl Jung once wrote, "Life really does begin at 40. Up until then, you are just doing research." Of course, Jung was not speaking about the cosmos, yet sometimes I feel there is a deeper meaning hidden within those words, because every journey has two parts, a beginning and a destination. Throughout our journey, we have explored the childhood of the universe, the Big Bang, the cosmic microwave background, the first stars, the birth of galaxies. But now we turn toward the old age of the cosmos, an old age measured not in years, not in millions of years, but in trillions upon trillions of years and beyond. A future so distant that ordinary language begins to lose its meaning. If our current understanding is correct, the main character of that future story will be dark energy, the mysterious entity we encountered earlier, the invisible component driving the accelerated expansion of space. Imagine standing on a vast shoreline at sunset. Before you are thousands of boats slowly drifting away from land. At first they separate gradually, but then the current grows stronger, faster, carrying them farther and farther apart. Eventually each boat disappears beyond the horizon. Something similar is happening to galaxies. Today, when we look into the night sky, we can still observe hundreds of billions of galaxies within the observable universe. But if dark energy continues to dominate, the distances between galaxy clusters will keep increasing. Space itself will continue stretching. The most distant galaxies will slowly disappear from view, not because they cease to exist, but because their light will no longer be able to overcome the accelerating expansion of space, one galaxy after another, one cluster after another, entire cosmic networks gradually fading from sight. A civilization living hundreds of billions of years in the future may look into the sky and see only its own galaxy. No evidence of the wider universe. No trace of the vast cosmic structures we see today. This creates a strangely emotional paradox. The universe will still exist, yet it will become increasingly lonely. Jung once wrote, "Loneliness does not come from having no people around you, but from being unable to communicate the things that seem important to you." Whenever I read that quote, I think of the future of galaxies. Not because galaxies possess emotions, but because the image feels strangely similar. The galaxies will not disappear, yet the distances between them will become so immense that light itself will no longer connect them. A cosmic loneliness, a silence lasting for quadrillions of years. Yet this is only the beginning, for another process is unfolding as well. Star formation will gradually slow. Today, many galaxies still contain vast clouds of gas, the cradles where new stars are born. But that supply is not infinite. Over time, more gas becomes locked inside stars. Galaxy collisions become rarer. Cold gas clouds become increasingly scarce. Then one day, not tomorrow, not in a few billion years, but in a future so distant, it is difficult to imagine, new stars will almost cease to form. The nurseries of light will fall silent. No new songs of the universe will be written. Only ancient stars will remain, old lamps burning through their final reserves of fuel, and one by one, those lamps will fade. Our own sun is no exception. Roughly 5 billion years from now, it will expand into a red giant. Later, it will become a white dwarf, a small remnant, still hot, but slowly cooling. The same fate awaits most stars in the universe. Less light, less warmth, more darkness, longer silence. Yet even after the last stars fade, the story does not end. For one class of objects may endure longer than almost anything else. Longer than stars, longer than galaxies, longer than nearly everything. Black holes, born from the gravitational collapse of massive stars and from the centers of galaxies. In the unimaginably distant future, after most light has vanished, black holes may become the final survivors, dark fortresses within an increasingly cold cosmos. Objects that once shaped galaxies, once consumed matter, once seemed eternal. Yet even they are not immortal. And here we approach the final chapter of the entire story. A chapter written in part by Stephen Hawking. A chapter describing something almost impossible to imagine. That even black holes may disappear. That even the most enduring things do not last forever. And that final step leads us toward what cosmologists call heat death. A state so cold, so dark, so still, that it lies beyond nearly every human intuition. And so our journey tonight slowly reaches its conclusion. Together we left Earth behind. Left behind the familiar sky. Left behind the stars visible to the naked eye. We traveled among distant galaxies. Passed through the ancient glow of the cosmic microwave background. Crossed the cosmic dark ages. Witnessed the birth of the first stars. Explored the mysteries of dark matter and dark energy, and finally glimpsed a future so distant that it nearly exceeds the limits of imagination itself. A future where galaxies gradually disappear from sight, where stars slowly fade away, where black holes silently evaporate, and where the universe drifts toward the cold stillness known as heat death. At first, all of this may make us feel small. Small before infinite space. Small before timescales measured in trillions upon trillions of years. Small before mysteries science has not yet solved. But perhaps that is not the most important lesson. Carl Jung once wrote, "Who looks outside dreams, who looks inside awakes." Throughout this journey, we have looked outward, toward the farthest distances from which light can bring us information. But perhaps the deepest beauty of studying the universe has never been merely understanding galaxies. It has been understanding ourselves. Because when we look into the cosmos, we are witnessing a remarkable story. A story that began with tiny quantum fluctuations, then gradually formed stars, galaxies, planets, life, consciousness, and eventually beings capable of asking, who are we? Where did we come from? What awaits us ahead? Perhaps that is what makes humanity special. Not because we are the center of the universe. Science has shown us that we are not. We live on a small planet, orbiting an ordinary star in the outer regions of an ordinary galaxy. And that galaxy is only one among hundreds of billions of others. But what is remarkable is this. The universe has produced a form of matter capable of becoming aware of the universe itself. After billions of years of stellar and atomic evolution, eyes emerged that could gaze into the night sky. Minds emerged that could wonder about the origins of stars. Souls emerged that could feel the beauty of a silent sky filled with ancient light. A quote often attributed to Carl Sagan says, "We are a way for the cosmos to know itself." And perhaps that is one of the most beautiful ideas science has ever offered. That we are not separate from the universe. We are part of it. The calcium in your bones, the iron in your blood, the carbon in every cell of your body, were forged inside ancient stars that died long before Earth existed. In the most literal sense, you are made of stardust. You do not merely live in the universe. You belong to it. And when we remember that, the great questions become gentler. Perhaps we will never know the whole truth. Perhaps there will always be horizons we cannot cross. Perhaps there will always be mysteries beyond our understanding. But that does not make the journey meaningless. Quite the opposite. Those unknowns are what make the journey worthwhile. And now, allow your eyes to grow heavy. Let distant galaxies drift slowly through your imagination. Let ancient stars quietly dissolve into darkness. And let the stillness of the cosmos guide you gently toward peaceful sleep. Good night, and may your dreams be filled with stars.